All right. Well, thanks for having me. My talk will be like Sylvain's introduction for a change in English. I prepared some slides on analytical approaches to the conformal bootstrap. I'm not going to make any pretense of completeness, so I already checked if there's good chalk. There's some good chalk. So I will probably need some chalk to back up what I put on the slides. I just wanted to give a bit of an overview of analytical approaches to the conformal bootstrap for the non-physicists in the audience. Yeah, there's some, I guess, some unfamiliar faces. So I hope for those people it'll be interesting. And you should all feel completely free to interrupt me with any questions and comments and so on. I hope we can make this a bit of an informal talk. So just to get everybody on the same page, I prepared 1 or 2 slides with very preparatory stuff. Of course, the conformal bootstrap conformal field theories are big objects, mathematically speaking. So I decided to just focus on 4-point functions of identical scalar operators in conformal field theories. So it's just a very simple structure in the end, and we'll see how this in the end reduces to just functions of 2 variables, basically. So we'll just look at a class of functions, essentially. That's what I want to get at here. So what is this class of functions? Well, it's defined like so. It's 4-point functions of scalar operators in reflection positive conformal field theories in d dimensions. So what are they? Well, they look like this, like expectation value of phi of x1 to phi of x4. But for us, they're just real valued C-infinite functions. Defined for now for Euclidean configurations. We call this Euclidean. So x1 to x4 are points in Rd. And they're defined away from contact points. They're completely symmetric in the 4 variables and constrained in particular by an action of SOD plus 1, 1, which is the conformal group in more than 2 dimensions. So in d equals 2, there's the Virasoro algebra, and there are many more constraints, in fact, infinitely many more. But I will not be using them. So what I say will apply to d equals 2, but you can get stronger results in d equals 2. I will also not consider d equals 1, which is a little bit sad, because what Dalimil discussed this morning is more closely connected to d equals 1, but I will not consider it. So there's this action of the conformal group, which is there by assumption. And concretely, this conformal group is generated by these transformations. So it's invariant under simultaneous translations, simultaneous rotations, simultaneous dilations, where you scale. So this is the scale symmetry of critical phenomena. And then there's one special guy, which is a conformal inversion, which means that they're invariant under so they obey this identity. Note that, of course, the conformal inversion sends 0 to infinity, so we really need the 1-point compactification on R4. That's where all of this is completely well defined. R4, not RD? RD, RD. So x1 is in RD or infinity, and same for x2 and x. So you need the 4th power of RD or infinity.
So covariant means they are invariant?
Well, covariant in the sense that sometimes they're invariant under translations, right? If I do a translation, nothing changes, but here there's something, so there's some factors, so I felt like more like covariant is maybe the more appropriate word. What else did I want to say? Yeah, there's this number here, delta phi, which is of course the scaling dimension of this operator phi, but for us, these 4-point functions are this delta phi is just some extra number that parameterizes the different correlation functions. And then since I have infinity, I can move a point to infinity by conformal inversion. That's the same as moving a point to the origin up to some factor. So this limit is actually finite because it's the same as by inversion as moving a point to the origin, which is by assumption finite, if the other points are not at the origin. So Well, then you go and look at the orbits of the conformal group, and you basically find that every allowed configuration of these 4 points just lies in the orbit of this very simple configuration, where you take all 3 points, you put 1 point at infinity, the other 3 they span a plane. On that plane you introduce complex coordinates z and z bar, you put 1 point at the origin, 1 at 1, and then the last point is free. So if for now, let's say that z bar is a complex conjugate of z, z bar is z star, which is a bit of a strange notation, but z and z bar is typical notation, and we'll later take z and z bar complex and independent. So that's the function we will work on from now on. We don't need these 4 variables in RD, we just need these 2 variables, z and z bar. And also, it's easy to see that this function is symmetric in its arguments. Now we get to the fun part, like the typical, the strange structure that these functions must have in conformal field theories. So they obey 2 properties, which is crossing symmetry and a conformal block decomposition. And instead of just introducing the full conformal block decomposition, I thought I would warm things up slowly and so introduce some consequence of the conformal block decomposition that I'll introduce with CB double prime. And later on we will have CB single prime, and then we'll have CB, which is really the full statement. So CB double prime is a consequence of the conformal block decomposition, but is not equivalent to the conformal block decomposition statement. So for us, as a first warm-up equation, we'll just say that the conformal block decomposition in particular implies that this function has this structure. And so this sort of generalized series decomposition, which is convergent in the unit disk, z bar less than 1. And all of these coefficients here, ck and these exponent h and h bar are strictly positive. And h minus h bar is an integer. So this immediately implies that this function that we had, which was defined for z bar equals z star, is actually locally analytic in 2 variables. So we now can take z bar and z star independent and complex. And that will work at least on the punctured bidisk, where z and z bar are both between 0 and 1. And so what I want to get at is basically that this is a game of analyticity and convexity. And the convexity here is because these coefficients ck are positive. So one way to see that there is some convexity property is you have 2 of these functions, then a convex combination of them is also 2 of these functions with such a decomposition, then a convex combination of them also has this decomposition. And then finally, there is the crossing symmetry, because we have these 4 points, but they're all 4 are the same. So in particular, of course, we can swap 0, 1, and infinity, but as a first approximation, so that's why there's a prime, we can swap 0 and 1, and that's basically the same as saying that G is invariant under this transformation. Yes?
Under which conditions C's are positive?
Reflection positivity, which is because they're the square of OPE. So I'll show you why. The coefficients of the so I set reflection positive, so I'm in the clear. But the conformal blocks have positive decompositions, and it turns out that the decomposition of the conformal blocks in these monomials is also have positive coefficients.
Is it true for all the CFTs or the non-unitary CFTs?
No. Reflection positive is in Euclidean signatures, unitary in the Lorentzian signature. So that's the space of theories I'm looking at.
So where did you use so far that h minus h bar is an integer?
I did not.
Okay.
No.
Well, the fact that it's single valued, no? Or
Sorry. Yes. H minus h bar must be an integer, because if I go to this configurations and I send z to e to the 2 pi I z around the origin once, the z bar must go in the opposite direction.
Go to which configuration?
This, where z bar is z star. Then I do z clockwise rotation. Z bar is the complex conjugate, so it does an anti-clockwise rotation. So you get this e to the 2 pi times h minus h bar, and that better be 1, because this function should be single valued when z bar is z star. Thanks. So we end up considering these type of functions. I basically just summarized what we wrote on the previous slide. And already this toy problem you can ask questions about. And it's already interesting. I mean, one of the results that I'll discuss is basically one for this toy problem, and it was sufficiently interesting to get a paper published. So if you have like ways to investigate this simple toy problem, it's already interesting, and I think it would be worthwhile to say what to hear from the more mathematically oriented people what kind of methods you would naturally try to use to investigate this class of functions. One question that we'll talk about, this is sort of a motivating example that I'll come back to at the end of the talk. It concerns the asymptotic behavior of these coefficients ck. For example, using for example, in some limit where h bar becomes very large. So there you would naturally, so the large h bar limit would naturally correspond to z bar to 1. And then by crossing symmetry, that's the same as z bar to 0. So we know exactly what happens in that limit. So in z bar space, the function looks like this. And you can ask, well, what does this really mean for these coefficients ck and these possible exponent h bar and the corresponding exponent h? Right? So you see that this function as z bar goes to 1, it needs to diverge in this specific power law form. And you can ask, well, how does the sum reproduce this divergent behavior? So the behavior is divergent pointwise in z, at least so you use this sum when z is between 0 and 1. So let's put z somewhere between 0 and 1, and then z bar approaches 1 from below. You should reproduce this power. And of course, I mean, you can look at this right-hand side, the leading term, and expand it. So you can say that, well, roughly speaking, you want this left-hand side to equal the right-hand side in some large h bar limit. But can we say something more precise and have some universally true statement, which then, of course, in the end, we're doing physics here. So ideally, we would like to compare it with experiment and in practice. The large h bar limit of the terms in this sum is not really tractable by experiment, but numerically, we can play some games, and we can definitely compare predictions that we can make analytically with these numerical analysis. So as I said before, so here is basically this statement that I wrote on the previous slide. So what concerns the z bar to 1 limit, I just expanded this power law divergent term. And here's the left-hand side, which is unchanged. And so, as I said, these summands probably agree more and more in some sense as h bar goes to infinity. But the precise statement is of course, at this point, we don't have any precise statements. So roughly speaking, you would expect the exponents to look something like this. So on the horizontal axis, I wanted to plot h bar. But h bar minus h is an integer, so it's usually nicer to plot just the integer. So large h bar is here going to the right. H is here vertically, sorry. And then you see these exponents that sit here up to this factor delta phi and z to delta phi, z bar to the delta phi. So the values of h are delta phi plus 1, delta phi plus 2, and then all the integer j's. So that's what you see here. These red crosses are the terms that you see from the expansion on the right-hand side. And on the left-hand side, well, we have whatever we have. I mean, it's just some bunch of coefficients. And so those, like you can imagine, are the green points, and they can do whatever they are. But the expectation is that at very large h bar, so here very large j, these green points start to overlap more and more with the red crosses. But the precise way in which this happens is an interesting question and not so obvious, right? In other talks, right, I've also used this plot, and I kind of deliberately sketched 3 trajectories with 3 different behaviors, right? The first is sort of the most naive expectation, where the green points sort of, for every red cross, there's going to be a green point. And so on, and then it matches better and better for large h bar. But maybe it's only true in the average. Maybe there's some red crosses where there's no green point, and maybe this set of gaps is infinite, right? Maybe there are infinitely many gaps, but on average there's a green point for every red cross. Yeah.
Is it important that you're keeping h finite, or should we expect some universality also when h scale?
Yes, of course. So I just took the z bar to infinity limit, but you can take z bar to z bar to 1 limit, but you can send z to 1 at a given rate, right? Compared to the z bar to 1 thing, you can take z over z bar fixed and send both to infinity. Yeah, you know this, right? You can get all kinds of interesting limits and corresponding, at least naive predictions for what these coefficients must do in that limit, and whether those predictions can be made precise. That is an open question in many limits, I think, but in certain limits we, of course, know. Yeah. But this is the one I worked on, so this is the one I'm going to talk about. I can also explain why it's a bit more interesting than just sending z and z bar to 1 at the same time. A bit more challenging. So. And of course, a third option that I wanted to discuss that I put here is that, right, the green points never really are exactly on the red points, but they're on average. They average out to the red points. So they just keep oscillating with some finite amplitude. And here, of course, I said something about the spectrum, the exponents h and h bar. We call that the spectrum, but the same something similar should happen for the coefficients ck. Right, so an interesting analytic question, very simple, right? You can explain this to any, well, I don't know, first, second year student, is how can we make this idea precise? And until fairly recently, we didn't really have good, complete control over, or a sufficient control, I think, over these asymptotics. I should say that, of course, this is all under the assumption that this first subleading term is suppressed as z bar goes to 1. So I'm not sure I wrote it. Yes, I wrote it, but I didn't say it. So the next term in the series as z bar goes to 1, which is the next term in the series here after the 1, if z bar goes to 0, that should be subleading. So you want the infimum of all the h bar to be strictly positive. And by symmetry, of course, h bar inf and h inf are the same because of the symmetry under z and z bar. Okay, so that was a bit of a simple motivating example. So my introduction hopefully conveyed the idea that analyticity and positivity are the kind of things that we, or convexity, the kind of things that we, those are the keywords that we should be using somehow to say something about to constrain this class of functions. So I wanted to talk a little bit about analyticity in the second part of the talk, and then we'll talk about dispersive approaches, which of course also has to do with analyticity and the large delta limit, which is the large delta phi limit actually. I'll explain what I mean with that. And then I'll talk about large spin, and we'll go back to this example in the first in the introduction that I just discussed.
Sorry, so far what you said did not really rely on positivity, did it?
No, but without positivity, I think it'll be extremely hard to say anything precise because there can be huge cancellations between these coefficients. And so without positivity, right, I only know how to make this idea, the idea I sketched here, how to make it precise using positivity. Technically speaking.
On the previous slide when you said that you can define the analytic continuation of G to independent Z and Z bar, and this was already because...
Yes. Sorry, not, yes. If you go back further, here, locally analytic in two variables on the punctured by disk, right? So what happens? I make Z and Z bar complex and independent. So both modulus less than 1, but I give them independent phases. How do I know that the sum, right, the terms in the sum don't conspire if I make the phases independent? The terms in the sum can conspire that for certain phases, the sum just blows up. But because the coefficients are positive and it's absolutely convergent, you're not going to get more, you're not going to get into any trouble. Although it's absolutely convergent, so maybe we're just fine. Yeah, maybe we're already fine. Yeah. No, sorry. Yeah, it depends on the kind of convergence that you demand, but if you demand absolute convergence, then actually you don't really need positivity, I think. Anyway, we'll see. We'll use positivity when we need it. Another thing I wanted to say is what?
Sorry,
No, but I think it's very natural to say correlation function physically has to be finite. And if it's finite, you show that it's analytic. The condition that correlation function should be finite and should be absolutely convergent, well, you can make this assumption, but it's not physically reasonable.
Fine.
Why should physics care about absolute convergence as such?
Okay, fair. Then the positivity is needed to define the analytic continuation. That is true. So there was a thing that now escaped me. The coefficients, I guess we don't. I mean, positivity is kind of important for lots of things, but in another. I think one obvious relaxation would be to say that these things are bounded from below, and then you'll probably have you can have a lot of fun also with that statement, but I have not investigated it, but people have made that assumption in other contexts and set results about it. No, bounded from below for all k, so there's a uniform bound in all k. And then I think it's fine. Okay, so this was my outline, so let's just talk a little bit about analyticity. So now I have a better statement, which is CB prime, which is 1 prime less, so it's strictly stronger statement, which is also a consequence of the conformal block decomposition that I'll write on the next slide. But I just wanted to introduce this decomposition. And it's done, so you see it's kind of a similar decomposition as we had before, with coefficients b that are positive, exponents eta and eta bar that are positive, eta minus eta bar is an integer, but instead of z we have this variable rho of z, which was put forward. Well, I mean, it's an old variable that appears in various contexts, and Slava and Matthijs way back in the early days of the Bootstrap introduced this as a natural variable for conformal blocks. So what is this rho of z? Well, it's just the map that maps this biholomorphically, the complex plane minus the cut from 1 to infinity into the unit disk. It fixes 0 and 1, so you see the map itself has the branch cut at z going from 1 to infinity. I sketched another branch cut from minus infinity to 0, which here in rho variables goes from minus 1 to 0. That's just because that's the branch cut of rho to the eta. It's not a branch cut of the map itself. Right, so of course, I mean, this is a biholomorphic map. If you have something expanded in z, you can also expand it in rho, and vice versa. Around 0, it's completely it has a regular Taylor series expansion, both the map and its inverse, so everything is completely normal. But so the stronger statement here is that these coefficients b are still positive. That's non-trivial, right? If I had omitted that constraint, I would not have given you any new information. But the coefficients happen to be positive, again, by physical arguments. They happen to be positive also in this rho decomposition. So now we can, of course, we know a little bit more. This is the stronger version of the conformal block decomposition that we'll play with in the next few slides. But first, just for completeness, the full conformal block decomposition is just another decomposition, again, with coefficients, I said it here, coefficients ak that are positive. So this decomposition is just reshuffling the rho decomposition, the rho variable decomposition. So the conformal blocks, so it's a decomposition in terms of conformal blocks with positive coefficients. These conformal blocks in themselves also decompose into rho power series expansion, where m and n now range from 0 to infinity, so it's just up to the initial fractional powers, it's just integer powers. And these coefficients f, m, n are also positive. They can be determined recursively because this conformal block obeys differential equations, so we have explicit recursion relations for these coefficients. And again, there's eta minus eta bar is an integer. So here the primes I just added for the conformal block decomposition to not confuse you with to not mix them with the eta and eta without primes for the rho decomposition. And these exponents are still positive. In fact, they're slightly stronger D-dependent constraints, but they're not important for what I'm going to say. So this lower bound 0 is not optimal. Given a space-time dimension D, I can give you slightly stronger bounds. And one other thing I should have put in the notation probably is that the conformal blocks also depend essentially, crucially on the space-time dimension D. So these coefficients depend on D as well. But again, the most important thing, I mean, if you just have a row decomposition, you can obviously decompose it into conformal blocks because, right, you can just replace the leading term and then subtract all the subleading terms. It's an obvious reshuffling, but this is a strictly stronger statement because this decomposition also has positive coefficients. And that is, of course, this is the strongest statement. So this is the statement CB, and this is the strongest statement of the conformal block decomposition. So we're looking at functions of this class. But again, I mean, if you don't like conformal blocks, you can already go back to this toy problem or the even simpler toy problem and try to say something interesting. And if you think it's interesting, it's probably also interesting for, well, at least for me, but for physicists, I would say. I had one slide on the numerical conformal block, numerical analysis. So the conformal bootstrap, or the numerical conformal bootstrap that was started in 2008, I have a slide on it, but let me skip it in the interest of time. So that conformal bootstrap numerical analysis, you can, it's of course, that's what started the whole revival of the conformal bootstrap back in 2008. But let me not go into detail. So let's forget about the CB, the strongest conformal block decomposition statement, and just go back to the simpler decomposition in terms of this row variable. So what does it tell us? Right? It's I think it suffices for analyzing analyticity. I'm not sure there's much more that you can gain using the full conformal blocks when it comes to analyticity that you cannot know if you just look at the row decomposition, the row variable decomposition. So first of all, of course, analyticity, right? This row variable is much nicer than the Z variable. Before we had analyticity in the unit Z disk or the bidisk, right? Z and Z bar each in their disk. But in terms of the row variables, we have analyticity in a much bigger domain, the pre-image of the unit row disk, which is basically this complex Z plane minus the cut at 1 to infinity, going from 1 to infinity. And of course, you can send rho around 0 as many times as you want. You have your branch cut at rho equals, I put it here. We have this branch cut from minus infinity to 0, but we can just go through it. That's just inserting phases. And because this conformal block, this decomposition is convergent and these coefficients are positive, you're not going to hit any divergence through these analytic continuations. So you can go through this cut at in the Z variables. And you can go onto the second sheet and a third sheet and a fourth sheet and so on. And you can do it in clockwise direction, anti-clockwise and so on. And the natural claim, the obvious claim now is that the 4-point functions are analytic on an infinite cover of this bidisk. And you can just go through this cut infinitely many often as long as you don't hit the cut. As I say here, you can go through the cuts infinitely often in any direction and you always find on the secondary cut the same domain of analyticity, which is the entire complex Z plane minus the cut going from 1 to infinity. Right? So that is our, and that's what the row variables buy you. They buy you this big domain of analyticity. But of course, right, this is just the CB decomposition, but we also have CS, the crossing symmetry statement. So we can ask, okay, how does this rhyme with crossing symmetry? Right, here's the statement from the previous slide, and the CS statement, or the weaker version of it, is just the CS prime statement. And we can just combine these two statements, and we see that this statement also clearly makes sense if you just interchange minus infinity 0 with 1 to infinity. So we can in fact also go through the other cut infinitely often. We can do it in the Z variable. Actually, there's also symmetry under Z and Z bar, so we can do the same in the Z bar variable and so on. But actually, I think we do not know the domain of holomorphy for these functions, or a domain of holomorphy. So this domain is not really a product domain, because once you send Z around 0, for example, so you go onto the second Z sheet, then the z bar variable is constrained to lie in the unit. You cannot send z bar around 1 at the same time because those use two different decompositions. To keep control, you would need two different decompositions. And as you send z bar around 1, you lose one decomposition. And as you send z around 0, you lose the other decomposition. So you don't have a convergent decomposition there. So at the moment, right, so it's obviously, I think it's fairly clear that the domain that we get in this way is not a product domain. And we don't really know what happens if we go into these weird regions. So I think Petr Kravchuk, I sent him an email, so he investigated this question and he said indeed that, so he claims that this is indeed what you get in the obvious way is not a domain of holomorphy, that there is a way to extend it a little bit at least, so it's extendable, but what the full domain of holomorphy is, we don't really know. And I feel like, right, this is a well-posed question, which again, you can explain to anyone who knows a little bit about complex analysis in several variables.
Is there any reason to expect that if you keep going through any cuts you want, for the two cuts in any order, then it will ever not be holomorphic?
I don't think so, no. I don't think we have an evidence of very singular behavior as you approach these branch cuts.
Oh, but I think physically going through these cuts, it has, in some cases at least, it can be given interpretation in terms of Lorentzian physics.
Yes, that is sort of, yeah.
And from the Lorentzian point of view, going through cuts, you mean crossing some light cones, and once you cross several light cones, why do you know that the function is still holomorphic? I mean, it's not guaranteed.
Right.
By general principles of quantum field theory. So I think it remains to be seen.
Right. But of course, right, by general principles of quantum field theory, now we have the general principles of complex analysis in several variables, and maybe we can say a bit more.
Yeah, absolutely. It's an interesting problem, I think.
Other results people have derived by assuming that it stays holomorphic after passing through, say, each cut some number of times, or that hasn't really been done?
No, not so much. I'll mention some applications where knowing this would be useful. Or one application. Okay. So this is related to what Slava's comment. So here again, some summary of what we know so far: CB prime, CS prime. Another thing that would be interesting to know is you just go onto a second sheet and then you approach the branch point or the branch cut again. And you can ask, well, what happens at that point, right? So we know on the first sheet, I already told you, as z bar goes to 1, things look like this. So what if I send z around 0 on the second sheet and then I send z bar to 1, for example? That's a different limit, and by this single valuedness, it's the same, right? You can set z around 0 clockwise and z bar anti-clockwise, and then you don't do nothing because that's single valuedness. So it's the same as looking at z bar to 1 on the second sheet. And well, what can happen there? For example, so at this type of branch point. Well, of course, if we go on to the second sheet, we insert just phases, right? We send z to e to the 2 pi iz. And so we just insert phases, and by everything else is positive. If we take z and z bar somewhere between 0 and 1, then rho also sits between 0 and 1. So this is all positive numbers, some phases. So it's not going to be then bigger than the thing without phases. So you get an obvious bound that on the second sheet things are somehow not worse than on the first sheet. And I mean, so this is just a simple analysis. In this paper, I think you guys showed that right, all the boundaries of the domain of convergence of this thing, there's some kind of bound that you can find, some power law bound, which basically says this thing may diverge at the boundary, but it'll also always be some kind of power law, something like this. And so there's a natural corollary of that, which is that the resulting value, the resulting object that you get at the boundary of the domain of convergence of this thing is a distribution. I hope I'm paraphrasing more or less correctly what you. So there's actually we know that it's a distribution, but as Dalimil asked, maybe it's much better than that, and maybe it can actually be analytically continued. Maybe it's still analytic, that we don't know. So you can ask, okay, well, right, on the second sheet, the behavior cannot be worse, the divergence cannot be worse than on the first sheet. But actually, is it maybe, right, can it be better? Can it be much softer? Naively, you would think yes, because you're just inserting phases, so you can get some weaker result. But in some cases, this is you can actually show that the behavior is neither worse nor better, it's just the same. So here's a little proposition, which is that if you send z bar to 1, and you cancel this leading, do I have it? Yeah, you cancel this leading power term, so I should just get the 1 minus z to the minus delta phi, which is this thing. This limit is true even if I first move z onto the other sheet, which is not entirely obvious, right? I send z to the second sheet, I send z bar to 1. To understand the z bar to 1 behavior, I needed to to look at the expansion around 1, z and z bar around 1. That's where this term comes from, and this term. But once I send z around 0, I'm not allowed to look at that expansion. That expansion no longer converges. But the reason this is still true is basically because of some nice theorem in complex analysis that we should have found a lot sooner in our field, I think. It's basically that this function, right, you should, well, I say it here, fix z bar somewhere between 0 and 1, then just look at this function as a single variable analytic function in z, right? So the limit as z bar goes to 1 for this, so you have a family of analytic functions in z labeled by z bar. Well, this limit exists for z between 0 and 1 because that's where we have the cross-channel expansion that converges, and it's exactly this thing. But now I claim that the limit and the analytic continuation in z actually commute, and that's just because the function remains bounded. And that relies on a little theorem by, Vitali, which follows from Montel's theorem, if you know that. And it just says that if you take a bounded sequence of analytic function, in fact, it can only be locally bounded, it's totally fine. You suppose that the limit exists for all z that belong to a subset of the domain of your interest. And this subset can be very small, but it must have an accumulation point. So it's not a few points, but here it doesn't also need to be like a full interval. It can be a discrete set or a countable set, but it must have an accumulation point at the very least. Then, as it happens, the limit and the analytic continuation commute, essentially. That's what this says. It converges uniformly in compact subset of omega to an analytic function. So this is a nice little theorem, and so we already know something more about the approach to these green branch point than we knew before, just using complex analysis techniques. So one of the reasons, well, we'll meet Vitali a few more times in the talk, but one of the things I want to stress is sort of, on the one hand, it's a nice result, and on the other hand, it feels a little bit weak in the sense that we have analyticity also in z bar, and we're just throwing that out the window. We just have, right, we have analytic function of 2 variables, and we're just looking at this as an analytic function in a single variable, parameterized by a second variable. So it would be nice to see if there's even stronger results if you just use some techniques from SCV. Okay, so that was what I wanted to say about analyticity. So there's some open questions. We have some minor results, but I think it's still nice to think about how the domain of analyticity and the approach of the branch points, using just these very general, very simple principles like CB and CS. Any questions?
Can you, so since you were talking about branch points and analyticity, can you extend this function over Riemann surfaces using some backing?
Yeah, but certainly, right, there's this Riemann surface which I try to sketch here, which is this universal cover of the bi-disk.
Then it will be analytic on the Riemann surface, right?
Yes, but a surface is, right, because we have two variables. So a surface is just a one complex dimensional thing, right? You have the same in Z bar. Now you take the union of those things in a way, right? And then, but then you still have to see if that's the domain of holomorphy, and if not, which, well, we claim it's not. Then you should ask, okay, what's then the biggest domain in C2, or some branch cover of C2, that's where I have analyticity. All right, no other questions. Good, so I always had a prime on crossing symmetry because I always forgot I only wrote this one. But of course, there's also swapping, say, 0 and infinity, which is also should also be a symmetry. So the full statement of crossing symmetry is CS prime plus this extra condition where, because the point at infinity had these weird factors, you see these weird factors in the crossing condition. And again, so technically this is initially true for Z bar equals Z star, but it works in a bigger region by analytic continuation. So the full statement of crossing symmetry, right, we have CB without primes, which was the conformal block decomposition. And we have this CS, which is the crossing symmetry, and that's the full statement. So that's the class of functions. So I'm implicitly defining a class of functions that depends on D and delta phi, that obeys CB and CS. And it depends on D and delta phi. Well, it depends on delta phi through here and on D and through the structure of the conformal blocks. So what does this new crossing symmetry equation buy you? Well, it says that actually these spins, well, these parameters eta minus eta bar that appear here, they're actually even integers. They're not just integers, they're actually even integers. We'll not use that, I think, in this talk at all. But it happens to be true. And similarly for the full conformal blocks, I had an eta prime and an eta bar prime, and those also, their difference should also always be even integers. And secondly, it implies that, right, there's some kind of boundedness as Z bar goes to infinity. Z in modulus goes to infinity, sorry, because this thing, right, that's the same as sending Z to 0, and we know what happens there exactly. We have the 1. So there's some boundedness as Z goes to infinity, at least in this region. So actually, right, now you have a function with branch cuts in the Z plane from minus infinity to 0 and from 1 to infinity, and the same for Z bar. And you have some boundedness at infinity, so the natural question that you can ask is if there's some dispersion relation, that you can recover the analytic function just from its discontinuities. Right, so that's the dispersive approach. You have a sort of bounded functions because this limit does not cover every different way in which Z and Z bar can go to infinity independently. But let's swipe that under the rug, as we all do in the physics community, which I'm not very happy about, but we do that. We have a sort of bounded function that's analytic in two variables locally. So is there a dispersion relation that expresses this function in terms of its discontinuity, right? Some kind of generalized, if you want a generalization that starts with a multivariate version of the Cauchy integral formula. So one, you can ask what type of discontinuities, right? I can just take the discontinuity in Z around 0, or for Z around 0, Z bar around 1, or double discontinuities in Z and Z bar both around 0, both around 1, and so on. And I want to motivate a particular type of double discontinuity that was, I think, first introduced by Simon Cauanuot in 2017. Which is this double discontinuity around 0. And I want, in the next slide, we'll see that these type of double discontinuities should suffice to reproduce the full function. And the reason this is nice is if you look at this particular solution, where you take, right, I swept it under the rug, but right, in this decompositions, there was always the 1. And so the game is to just take this 1, and then take its images under the crossing symmetry. So you get two other terms, which is the one and then the two others. I mean, the one with the prefactor and then the two others under crossing symmetry. And that is, as it happens, a good solution to both CB and CS. It has positive coefficients if you decompose it. And it obeys all the constraints. So this is sort of the simple solution that every kid learns. In CFT kindergarten, you learn that. And then, right, you add, so you can ask, okay, how can my function deviate from this very simple solution? So this is also called the connected correlation function for reasons that should be obvious for anybody who knows quantum field theory. And so this connected correlation function, it would be nice to decompose, to find some kind of dispersive approach to this connected correlation function in particular. But of course, if you just subtract a bunch of stuff from the full correlation function, then you cannot claim that this connected correlation function has positive coefficients anymore. And positivity is kind of a nice thing to have for reasons that we'll see later also. So that is why this double discontinuity that I introduced here is particularly nice, because it retains positivity for z bar less than 0. So what happens is that if you take a monomial, rho to the eta, rho bar to the eta bar, and you compute its d-disk 0, well, it's just, right, you go, so z and z bar are supposed to be both negative here, and you go either below or above the branch cut in this particular combination. Well, you get some e to the I pi etas and eta bars, and then there's some delta phi's, because, that I missed. Sorry, this should be eta minus delta phi, and eta bar minus delta phi. Or it should be z to the, no, this is where I need to chalk. Then this is also why these rho and z variables are not rho z to the eta. And then the same for z bar. And this is what you need. And z bar to the minus delta phi. Rho z bar to the eta bar. So that is the term I should have written. And that will give you as a double discontinuity. It will just insert, if you simplify this, it'll be a sine squared of pi eta minus eta bar minus 2 delta phi.
So why is that the bar less than 0?
Because otherwise there's no discontinuity, right?
Oh,
okay. No. So, and sine squared is of course non-negative, so that's nice. And furthermore, if you decompose these gadgets, these things that I added, that you have to subtract to get GC, then you will find that for all of these gadgets, the values of eta and eta bar that you get are precisely 2 delta phi plus an even integer, so that this sine squared is always 0. So for the double discontinuity, so in other words, the double discontinuity, well, this is the 1. So in the rho expansion, that is just a leading term. But these terms, they have their double discontinuity around 0 for both this and this is just 0. And you can also just see it not just by decomposing them, but just plugging in the numbers, right? This one doesn't have a branch cut at 0, and this one doesn't have a branch cut at 0. So it has 0 double discontinuity. So the double discontinuity of GC also has positive coefficients. That is the lesson here. So you can ask, okay, well, GC is kind of bounded at infinity. It has the same branch cuts. Can we reconstruct GC from its double discontinuity around 0 and also the image, the double discontinuity around 1? And of course, right, you would expect the answer to be yes if the behavior at infinity is sufficiently smooth, because it's kind of saying that if the double, you can ask, well, what if a function has 0 double discontinuity around 0 and 0 double discontinuity around 1? Then roughly speaking, it's analytic around 0, it's analytic around 1, and then you won't expect, right, if it's also finite or goes to 0 at infinity, then there's no room left to for any non-trivial function, so you just get 0. And as it happens, there does exist a conformal dispersion relation, which is does exactly this, the job of reconstructing the full function from integrating the double discontinuity. So here the conventions are a little bit all over the place. I'm not sure this is exactly correct, but in spirit, this is definitely the right equation. You reconstruct GC from its double discontinuities on the left and the right cut. And this kernel is extremely strange. I would love to have a better explanation of this kernel. This kernel itself, the easiest way to write it is as a discontinuity in W in its of this kind of thing. So I think this is the kernel for the left bit, not for the right bit. But you see what happens. So it should be a function of 4 variables, z bar, rho, w, and w bar. And they enter in these crazy combinations. And then in particular, there's this hypergeometric 2f1, which involves this particular, which has as its argument this particular strange combination of w, well, rho of w, rho of z, rho of, with rho bar of z, I mean what I wrote rho of z bar before. So it's this particular combination that enters in some magical way, and that's and this is the kernel that is supposed to reconstruct the full GC from its double discontinuities. This x, right? It's a function of 4 independent variables, and in one way of writing it, x in itself is a cross ratio of the 4 variables, but those are cross ratio. Those were written in terms of cross ratios. So it seems to be some cross ratio of cross ratios, and we don't understand where it comes from. At least I don't. I think nobody does.
How did they derive this?
Yes. So how, right? They're clear open questions. Well, one of them is what can you do with this? How does constrain the physics? We know some results, but another question that we can talk about for the remainder of this slide is why this form? Where does it come from? And what Simon Caronio did is basically he used an old result on harmonic analysis to write some complete basis of a complete, that stated a complete basis of functions for basically functions roughly of the form that we're looking at, but I think it's a complete basis mostly in the L2 sense, so it's a bit weird because we're looking at analytic functions, but there was no real analyticity in those results. And then he found that sort of, so you have a complete basis, so you have some so like a Fourier decomposition. So you have some coefficients in the Fourier decomposition, or at least a spectral density. And he found a way to express this spectral density in terms of the double discontinuities using some contour pooling. And then from the spectral density, you can go back to position space. So that's basically what he did. So he combined, right? There's just a Fourier transform, and you write the function as Fourier transform and inverse Fourier transform, or decomposition and inverse decomposition. Then you do some contour pooling, and then you get this. So it's really, it's a crazy procedure, and right, the question for me is like, if someone says, asks this question, can you reconstruct these functions from its double discontinuities? My natural inclination would be not to try something involving harmonic analysis on the conformal group. I would probably start from some Cauchy formulas or whatever, but somehow that's the thing we needed to arrive at this formula. And I think it's still a bit surprising, because in none of this do we really need conformal blocks. And in this harmonic analysis thing, conformal blocks are really central. But we just needed this analyticity properties and this row variable decomposition. So CB prime was completely sufficient. The one with the, do I have it? Well, somewhere. CB prime. This is completely sufficient. We never needed conformal blocks. to ask the question, right? To make the question well defined.
Does this kernel satisfy some differential equation, this K?
Yes, yeah, all kinds of, yes, for sure.
Which is related to some Casimir of the conformal?
Yeah, there's some commutations with the Casimir. It commutes in some nice ways with the Casimir of the conformal, which is another way of asking why, right? Like why that is the case is another way of saying why do we need this kind of conformal symmetry or conformal blocks.
Was this ever fully placed in the Mellin space language, or only partially?
No, Dalymil has a very nice almost derivation of this thing in Mellin space.
What does the kernel look like in that language?
Yeah, it's a triple. Well, in the end, the kernel is a function of these 4 variables. So you cannot. I guess, okay, one thing you can say is how in Mellin space can I reproduce the Mellin amplitude from the discontinuity. And there, of course, what Dalimil showed is that it's just a discontinuity, it's a dispersion relation in Mellin space.
It's just the usual Cauchy integral formula in Mellin space. Okay. In Mellin space, it's super simple. It's like the simplest dispersion relation you can have, but it becomes this horrible mess when you go to position space.
But of course, in Mellin space, right, then there are all kinds of questions about how well-defined Mellin space is, because accumulation points of poles, and you're analytically continuing into domains that you don't really.
So this doesn't depend on dimension?
Right, no.
Yeah, so it seems to have nothing to do with conformal field theory. It's a theorem in complex analysis, right, which doesn't depend on SO1, D plus 1 in any way. But no one knows how to derive it properly without committing to some D and using harmonic matrices of SO1, D plus 1.
Anyway, how much time do I have? Oh, I'm out of time. So, okay, so I had some applications in mind about scattering amplitudes that I'll skip. Let me just say this. I'll just skip all the details and say this. So one mathematically well-defined question I think that I find interesting is if you consider a family of these functions that obey our axioms CB and CS, and they're labeled by some parameter R, which is some real number, and I don't have time to go into it, but it's just quantum field theory in ADS, if you know what that is. And I want to know what happens as R goes to infinity. And the constraint I give you is that as R goes to infinity, delta phi goes to infinity, D is always fixed, and the infimum of eta k and eta bar k also goes to infinity. What I should probably say is that they go to infinity at the same rate, so the ratio is constant. So, right, this is a well-posed question, and I want to know what can happen. Does this limit exist? Probably not, right? If you give me any family, the limit should probably not exist, but you can ask, well, is there always a convergent subsequence? Can things diverge, or do things have to remain finite? And when I say things, I mean, right, I can say all kinds of ways in which this limit can exist or not exist. Pointwise in Z and Z bars, pointwise in some domain, locally, uniformly, so you get analytic functions and maybe in the sense of distributions and so on and so on. And that's what I'd like to know because it offers a new approach to scattering amplitudes. That is something that I skipped on the previous slides. So this makes contact with old results, in particular by Bose, Epstein, and Glaser from 1965, who found some analyticity results of scattering amplitudes using the Weidmann axioms and making use of causality. And I feel like this is a nice approach because you have analyticity for any finite R, and you just want to show that the analyticity survives in the large R limit. So in that sense, it's a very different approach to a very old problem that people worked a lot on in the 60s. So feel free to ask me afterwards about why this connection exists. And then finally, let's go back to our toy problem. I just want to say a little bit, because this is supposed to be also a research seminar, so this is the research that I did, which is very simple in the end. I want to say a little bit more about this toy problem. So we just have Z and Z bar. We go back to those variables. We are working in the bidisk in the Z and Z bar variables. And we had this problem that for large H bar, things should look a bit like this left-hand side should look like this right-hand side. So there's actually a simple 3-step argument that tells you one way to make this precise, that this left-hand side should somehow, or the coefficients and the exponents in the left-hand side should somehow become those of the right-hand side. So the first is a Tabarian theorem, right? The game here is we want to kill both Z bar and Z, right, in favor of saying something about the C's and the H's and the H bar. So the first thing I'll do, and this is again sort of admitting our weakness, because we are again going to consider z bar as just a parameter, and we're just going to use analyticity in z. So the first step is z bar is a parameter, and then there's a family here of functions labeled by z bar, and you can just use a Tauberian theorem that says that as z bar goes to 1, these two guys agree, and then you basically want to say that, well, the summands themselves should also agree, right? Here you fix z, so it's just pointwise in z. So you fix some z, you see some z bar series expansion with some positive coefficients. Here some z bar series expansion with some positive coefficients. And then standard theorems, standard Tauberian theorem says, well, these coefficients on average should become the same. So on average, that means I should sum them all up to some large cutoff lambda. And then if I sum these coefficients up to some large cutoff lambda on the left, then that's the same as summing all these coefficients for up to some large cutoff lambda on the right. And so this tilde lambda to infinity sign means that the limit of the ratio is 1. Of course, here on the right, I can just do the sum because it's very easy. So you're supposed to get this lambda to the delta divergence, and then this type of thing for this 1 minus z to the delta, which looks like this. So now we have a result that holds point by point for z between 0 and 1. And it's not quite enough. And this is sort of where this limit was challenging, more challenging than the limit where you send both z and z bar to 1. And you can just directly use the Tauberian theorem to get your final result. Because we still have the z variable and we want to get rid of it. And so this is where Vitali's theorem again comes in. Because this result, well, we had it pointswise for z between 0 and 1, but again, if I insert phases, I send z to e to the I alpha z, this is not going to diverge. And so here we have analytic functions labeled by lambda, analytic in z, and I'm just saying that the analytic continuation and the large lambda limit should commute. Because things, right, a family of analytic function, it remains bounded, you can commute. So we've seen that before. So that is super nice, because then you can just play a little game where you just sort of inverse Fourier transform. You said z equals e to the I phi, maybe with some modulus less than 1. So z equals 1/2 times e to the I phi. And phi can be an arbitrary real number, right? You can go on any sheet. So you can just inverse Fourier transform with respect to phi to fish out the values of h that appear. And if you want to do it properly, you want to basically introduce some compactly supported test function phi of h, var phi of h, which is not our original operator. And then you can play these kind of games. So you say, well, what is this thing? This is obviously equal to that. And then this delta function is just the Fourier transform of e to the 2 pi I, or e to the w h k minus h. So you have some w that goes from minus I infinity to plus I infinity with some negative real part. And so that's what this contour is. You write all your integrals out and then you just get this. So this is all very elementary, but this is just the left-hand side. But the game is now, the fun part of writing this is now that you can take the large lambda limit inside the integral. And this here inside the integral, this is where lambda enters. That is just this left-hand side. So we set lambda to infinity, we cover this thing. And the only constraint on being allowed to take this limit inside the integral is just some smoothness condition on phi of h.
You cover which thing, because sometimes it's not clear like where you
Oh, sorry. So, right, I want to take the large lambda limit of this thing. So it's summed over h bar up to some lambda and smoothed it out in h space with some test function.
Yeah.
Then I do this trivial manipulations. Then I have this thing here, which is exactly this, where about z equals e to the w.
Yeah.
Thanks. And then, right, now I claim that the large lambda limit, I can take it inside the integral under conditions that this thing falls off at large imaginary w. And this thing falling off at large imaginary w, well, that's just a Fourier transform. So it's just demanding that this test function is sufficiently smooth. And then this thing, that suffices for this Fourier transform to follow. Thanks. And so you can take the large lambda limit inside the integral, and so you get a prediction that says that the large lambda limit of this guy is equal to the right-hand side. So you see, and phi of h can be compactly should be compactly supported and sufficiently smooth. So you get a nice little result, and it basically, I think the most important result is that the kind of averaging you have to do here on the left-hand side to get a mathematically rigorous statement, right? We had to sum over all h bar up to some lambda, so we're really averaging over a big window in h bar, and we're averaging over h space with some small test function. But we still cannot take, of course, pointwise in h this would not work, but averaging with a compactly supported smooth test function, we are allowed to take we get a result where we are allowed to take the limit. And so one of the immediate consequences of this thing, right? You see here there's a divergence, and all these coefficients are finite, so you better have infinitely many terms to reproduce this divergence. But if I take phi to be very compactly supported around, say, delta phi plus 3, m equals 3, right? This divergence is non-zero because this is non-zero. So there must be infinitely many terms that are supported around delta phi plus 3. And that's what this statement is. It must be infinitely many terms around delta phi plus m for any m in m integer, non-negative integer m, and for any epsilon greater than 0. Which strengthens an old result, of an older result by these three people who found the same result, but for m equals 0 only. So this is kind of a nice result, but I stated the objective that I want to compare with numerics or experiment, and this is an asymptotic statement. So I think it's nice, but it's not completely nice enough because I'd really like to say something about finite j or finite h bar. And in other contexts, we have some results, and it would be very nice. But maybe a little bit hard to say something about finite h bar.
You still cannot distinguish these three possibilities, or you can.
These three things, yeah, so this one is excluded, right? Because it keeps oscillating with finite amplitude, that's excluded. This one is not yet excluded by this result because we're averaging over all h bar. So it's still allowed if, right, the coefficient here may be a little bit bigger to offset the gap there, and so on and so on. So this scenario is not yet ruled out, but I think we'll rule it out soon. And so I think there should really be a large j limit that exists. But that's still not the same as saying something about finite j or finite h bar. That would be very nice. Okay, so I guess implicitly in this talk, I tried to define this for you, this class of functions, which is just these functions g of z and z bar that obey this conformal block decomposition and crossing symmetry, and they depend on the space-time dimension d and delta phi. And constraining what can happen in this space of functions is the same as constraining the physics of conformal field theory. So I think it's interesting. We can get some analytic results, mostly by taking various limits left and right. But I think, yeah, there are obviously many open problems, and also we are just, I mean, I feel like sometimes a bit like an amateur trying to rediscover tools that people, especially who know several complex variables, know very well. So I think there's lots of room for improvements, especially in the methods we're using. And it is fine, I think, that's another message I want to convey. I think it's fine to just consider the toy problems first, the CB prime and CS prime, the things I mentioned before. You can already get interesting results. And one particular point I want to stress is that we're not using analyticity in both z and z bar together. We're just doing analyticity one variable at a time, with maybe the conformal dispersion relation as a notable exception. All right, that's all I had to say, so thank you.
Just to go back to the Mellon space theme for a second, because I know you've also worked on that. Even if there are still things to work out foundationally, non-perturbatively, although there's been some work there. There are some complex analytic properties of those amplitudes that seem useful, and I know you've thought about that. Do you think that studying position space and Mellin space in concert might be useful, or are you just committed to position space, or what's your perspective on the right tools to try to use?
I think of course I looked at Mellin space. I think my starting point is this, right? So I'm starting in position space. And so if I want to use Mellin space for something, I first need to show that Mellin space, right, at the same level of rigor that my last two papers were at. I need to show that Mellin space exists and everything is fine in Mellin space. And that step,
of recovering this dispersion relation formula, can't we just pick some GC, pick GC as nice as you can, as you want? If you just want to understand what the kernel is, like pick some very nice GC for which Mellin space is defined.
Yeah. I guess so.
Is it a valid approach?
I guess. I mean, you can take it to be u to the s, v to the t, right? These kind of. And then, but then, of course, you want to do it for a class, right? You want to define some basis of. If you want to prove it in full generality, you want to define it for some basis of functions, right? Yeah. Not one function at a time.
Yeah.
And so maybe that's a good basis, yeah. But it's not quite the same as the conformal block decomposition. Right? This thing in itself is, because the conformal block decomposition has this is 1 minus v to some power. It's an expansion in 1 minus v to 2 powers. And so this is sort of going around the other end, whereas so I'm not sure it's the right basis.
But based on what Dalino said, seems like the right approach is to do the detour through the Mellin space, just like
right.
To make that part of the argument rigorous and then extend by completeness to the full.
Yeah, but then you have to show analyticity in Mellin space, right? Which is a bit, I mean, we discussed this, it's similar to analyticity in, I mean, you run into the same problems as showing analyticity in the spectral space, the analyticity of rho j of delta in delta.
I'm just saying how to recover that kernel.
Yes. I mean, then, yeah, you get, if you just assume analyticity, you get an integral expression for the kernel, which is a triple integral. Mm-hmm. And it's maybe less messy than the expression I showed. I'm not sure it explicitly shows why this variable x appears, because you get some kind of combinations. So you get some combinations of, right, you have u, v, and u prime, v prime, and you get some combinations thereof. I'm not sure you can really see that x is somehow an important variable.
Yeah, it still doesn't give any very conceptual reason for why the kernel looks different. It feels like this 2f1 is a preternatural function, some kind of uniformizing function of some surface maybe. So
yes, exactly. It's not just any 2f1.
It looks like it. Maybe if you still work in position space, but in some different positions, like change the variables, there's maybe some better.
Yeah, I don't know. So I was more looking. It's right that maybe in Mellin space. Well, it's good to know the Mellin space argument. Let's say that. But it would also be nice to have some position space arguments, right? There are several multivariable dispersion, multivariable generalizations of Cauchy formula. You can start from those, and try to see if there's something, some contour pooling you can do to get to this type of expression.
Excuse me. Do you want, I mean, by implementing these constraints, this conformal block and this swapping symmetry or
crossing
symmetry? So do you want to Are you looking for constraints on the powers on the exponents eta k or hk, or do you assume that these are given and then you are looking for the coefficient ck?
It's mostly. No, I don't think we can assume that the coefficients are the powers are given. So
are you looking for constraints on the coefficients on these powers?
Yeah, or these type of mixed constraints, right? So what I wrote is I mean, there's of course numerical constraints. The numerical conformal bootstrap. You should probably ask me afterwards if you're not familiar with that, because 99% of the people here are. Right. So here's a statement. Right. So this involves both the C's and the H's, and it mixes everything basically. Right.
No, but I guess the question is, for example, for a mathematician, do you have a proof that this space is not empty that you are studying it, apart from this mean field theory solution, which is GC equals 0? Do you know any function which lives in this space?
In d equals 2, we know a lot of functions. In d equals 3, right? We know almost nothing, I think, or none. Apart from GC equals, well, maybe some other simple versions. Sorry, we probably have a couple of simple examples, also in d equals 3. And they're coming from free fields, or right. If this phi, this operator that I wrote, is a free field, it's easy, but you can also take it to be any composite operator in the free field theory. So there are a couple of easy examples. But for example, in the conformal field theories of interests, these etas, I mean, some of them are known. These C's and these etas, we know a handful of them, maybe 100 or so nowadays, a few hundred, with some numerical precision. And we expect, right, our numerical analysis, everything indicates that these few hundred numbers can be completed into a full function. But for that, I don't think we have a proof.
You know what is missing from your talk, Balt, compared to Daniel's talk? You missed assigning all these names. Like, you had to call this set of functions something like Rastelli forms. Yes. And then you should have to introduce like a hierarchy of bounds. That would be like Van Rees bound, I don't know. And that we cannot prove yet. And then there is something else that would be, I don't know, Pal bound. That we already proved. Plus epsilon. Then I think it will be more clear what we're doing. No, but I mean, jokes aside, I think it's a very interesting set of functions that I think you know a little about, you would like to know about. And we're trying to get at it from various angles, numerics, analytics, and indeed you could say that these results that Balt showed are analogs of all these conjectures about L functions. I mean, can you say this? Can you say so that this is our analogs of conjectures about L functions?
I guess so, yes. It's yeah. Do you want me to say it on the record? No. All right. Yeah, I'm not a mathematician, so I didn't want to name things, or even I only talked about. I was wondering whether I should introduce this nomenclature, this curly C in the first slide or the last slide. I was a little bit worried that it would be too pretentious for the first slide, so I wrote it on the last slide. But it would be nice to know more about this class.
Is there anything to do in the non-unitary case?
Yeah, well, yes, non-unitary conformal field theories. First of all, you have to tell me what it means, because it's too wild, right?
No constraint on the CK.
That is a very narrow generalization of right, when you say non-unitary. Yes, right. So, okay, if you say the C's are not positive, it seems much harder. And, right, because already these results about analyticity are hard. So maybe you want to then assume analyticity, right? Say it's absolutely convergent, even though I don't have a very good argument for it. And then, but then you're sort of, right, I feel like the problem is that you have so many degrees of freedom if you say non-unitary, that maybe there is somewhere in this big world there's some interesting narrow subset of functions where you can say some interesting results. But that seems to not be the right way to go about things. You want a specific theory or a specific class of theories and then say, okay, this is what the coefficients can be, and then we can, or what the values that the coefficients can take. This is the domain of analyticity, these are the etas. The values that the etas can take, and then maybe we can try to say something. And of course the class of reflection positive conformal field theories is huge and super interesting, and so that's why I think this class is the nicest place to start.
Yes. You expect theories where you have a continuous family of H?
Yeah, sorry. Yes, of course. I guess they exist, but for most of what we are doing, we have some discrete spectrum, right? I wanted to write this at some point. Yeah, but of course, yeah, you know very well, thanks. There are solutions, not technically to CB because you don't have the identity operator in the Liouville theory, but solutions to similar things where eta is a continuous quantizer. Are there, with continuous spectrum, you have some solutions? Okay, if you...
No, it's a question.
It's a question. Yeah, I'm not aware of any.
I think there are conjectural generation of Liouville in hierarchy.
Yeah, so then this... Yes, so then, right, you would have continuous family. So instead of what I wrote, the sum over k in this conformal block decomposition, like here, the sum over k, you would just have an integral. And you would have some continuous family where eta and where h and h bar or eta and eta bar vary, and the same for c very continuously. Yes, I mean physically again you're sort of trying to find theories to which there's a definite class of theories that obey these constraints with the discrete spectrum. So I feel like it's fine to just look at that, but yes, obviously there might be exotic solutions.
Are you actually using discreteness?
I used it for I mean not always. I guess you can. I think here you need discreteness, but to prove that I needed discreteness, I think. But in the modular bootstrap, I don't think we use discreteness.
We just need a gap and that's it.
Yeah.
Also here we can remove the sum, at least for monomials, right?
Yeah, so the claim seems to now be that we have in our upcoming work we'll probably say that you're able to just fix h bar to some large lambda fixed value, or j to some fixed value, and then the large j limit works. So it's a limit without the sum over h bar. Yes.
My question, so when you look at 2D CFT, there is a correspondence with 3D topological quantum field theory.
Right. Already, yeah, there's some connections for some 2D CFTs, right? I think it's just, for me it seems like one of these consequences of having Vera's or conformal blocks or an extended chiral algebra, let's say, which means that there are much bigger conformal blocks because the representations are much bigger, and then you have the typical way that these topological field theories arises is because you have some braiding matrix in it, some finite matrix of these blocks. But if you don't have finitely many conformal blocks, then I feel like things are, I don't see a way to introduce a topological field theory that can be useful to study some of the physics of higher dimensional
conformal field theory.
But in principle, there should be some conformal field theories which appear on the boundaries of high-dimensional topological insulators, and this should be true in any dimension. It's just there's probably much smaller supply on these non-trivial topological insulators in high dimension.
Fair.
So this connection so far was not very useful for this.
Yeah, but it's not the same kind of there are certain quantum field theories where there's a connection to topological field theories in one dimension higher, but on the other hand, it's not the same kind of universal story where you introduce this modular tensor categories and so on. That seems very universal for rational conformal field theories. For every rational conformal field theory, or every class, you can introduce some TFT like that.
No more questions? Well, thanks again, Balt.